that I'm checking on, yes. At the last NCSL meeting, when they put my talk into the computer, they put in like revision 2. The one I was using was in my head was revision 10. And so I started, and after about the third slide, I looked up and saw that shouldn't be there. But I had already started. And so then I basically talked about whatever slides show up. And I'm not sure anyone noticed that was different than my normal talk, my coffee cup. This is not my talk. This is from Jack Stone. I don't usually give other people's talks, but in this case, we're going to talk about measuring small holes. And I thought that would at least be appropriate here. Okay. You know how much it costs to get the ground out of here so you can have water? That's why it costs so much. Jack Stone, who was our laser guy, he built one of the few automatic locking iodine stabilized lasers. He's been working with the fiber lasers and the laser cone. And in his spare time, he just thinks a lot. And this is his probe. The idea is an attempt to make what we have is better. This is the principle of the fiber probe. It's an optical fiber with a ball on the end. Now we send in light from this side, and there's a microscope. And it's interesting though, but when you shine light through glass, parallel light, it actually focuses with a line right there. The focus is very small. So when you look at it with your camera, you can magnify that line really big. So if I look at this and I see a fiber, I see a line that's about 5 pixels wide. The actual fiber would be about 30 feet. So you in a way of basically magnifying where this thing is in space, so you can see very, very tiny motions, even though the fiber's kind of big. The fibers, we started at 125 micrometers, we've gone down as low as about 50. And this is the image, and there's the image and the line. The real image is kind of cool because what he has is 2 cameras looking at it at the same time, and both cameras make up one line, so you can see sort of both directions at once on the screen. Waste not, one not. We only need one monitor. And so that little line there, as soon as the probe hits something, it bends and you can see it move.
John Whalen, Lauren from Sandia. John Whalen, Lauren with Sandia.
Now, the calibration is very good. This is running it up against a laser, and that's about 110 pixels. And in the bottom is micrometers. You can see, you can't possibly see that the end of the scale is 18 micrometers. So we're talking with a scale that's very, very linear calibration curve. We're measuring things that are very, very small. This is pretty much with 10 runs, because if it works once, the only thing you can do now is run it 10 more times to try to figure out what's really going on. This to that is 40 nanometers. There are 40, a micrometer is 1,000 nanometers. 40 nanometers is a little bit above, almost 2 microinches if there are any inch people. If there are any inch people, I apologize because I don't do inches. It's too hard to think both ways. When I go home, I only think in inches. So this is the system. Once it worked in one dimension, he built model 1. The fiber stood up this way. Version 2, we made the fiber move that way. We made it smaller. And so you basically have one camera, 2 lines. When you move to the side, you wait till one of them moves. That tells the coordinate measuring machine, stop, I'm there. And it records where you are. Now to use something this precise, you need something to move it on. And on the right is the Moore M48 coordinate measuring machine. It's about $2 million worth of hardware and controllers in a room that holds 10 millidegrees. And in fact, we never make measurements if it's not between 19.995 degrees and 20.005 degrees. It'll hold that 1 millidegree all day, and so on a good day. And this is the probe. And you ask, isn't that an awful large probe? They have this little tiny ass thing come out the bottom. The reason it's that is that the normal position where the machine is arrow mapped, the other probe touches here. And so if you want to use the arrow map and make corrections, all of your probes have to be this far below the rail. Or you have to make corrections, and we really don't like making corrections. So, there was obviously a lot of stuff like, does it bend? I mean, there's not much to it when you think about it. And it turns out not much. It's fairly long, and it's well behaved. There are other things, though, as once it's bent, as this pushes this way, so it ends up with a little bit of torque. What does that do? And it turns out that doesn't do so bad either. How about air? Well, that is a problem. So we ended up covering it up where the air could get with a cardboard box. That sounds strange, but the normal probe we use for making measurements has an active outer edge, and so it also lives in a cardboard box. The last thing is tough because this is glass. It can get charges on it. When you bring it near a metal surface, it sees the image on the other side, and it doesn't do quite what you expect. In fact, if it touches, it can stick. Then when you back off, it stays stuck to the side. Now, the room admittedly will keep 40% relative humidity all year long, but it has turned out to be a problem off and on. And here, we're measuring a 5 millimeter sphere down to a 1 millimeter hole. These were measured by us and pt.3, which is the German National Laboratory. They have a machine. They have a fiber probe also. Their fiber probe comes out and bends down, and they have a microscope to look at the ball. We look at the stem, they look at the ball. That's the major difference. Turns out it's nicer to measure this probe because the balls eventually get too small to really see well. And you can see the differences in micrometers between us and them. 60 nanometers, 40 nanometers, 50 nanometers, all given with an uncertainty of about 100 nanometers. No one else can do this. And of course, you can see things out around. So now the question is, you've got this ball on the end of a stem. Well, there's not much space between the ball and the stem. Does the stem interact, say, with the wall? And we knew this is a problem on other machine. We have a Metrology UMAP, which has a vibrating probe. And we kept seeing funny things, and it seemed that the calibration depended on the humidity. Never seen an effect depend on the humidity. And what happens is it vibrates. It doesn't actually touch the surface. Every surface has a layer, a thin layer of dead air. If you'll notice, your fans collect dust. Why is that? You would not expect a fan blade to collect dust. But the airspeed at the blade is 0. And so there's a little layer in here of air that's viscous. And so the probe gets close to it, and it almost touches, but when it hits the viscous layer, it'll tell you something's changed. So you have to calibrate that out. Like I said, we're dealing with little tiny things here. The UMAP has a 30 micrometer sphere and a 20 micrometer stem. Well, that means there's only 5 micrometers this way between the stem and the ball. So now the stem interacts with the layers. And every hole, the deeper it goes, the easier it fires, and everything looks this shape. It's a beautiful machine, except that it has this error in it. And there's no real way to get out of it except to calibrate some other hole and use that. So, this is an optical fiber connector. 125 micrometer hole in it because that's the size of optical fibers that go to your house. And it's about 6 millimeters. And what we did was, started at one end, went down, started at the other end, came up. And those are the runs at the top. And here, and then here from underneath. So we can go down 6 millimeters into a hole and still have about the same accuracy as we had before it went in the hole. Now, what can go wrong? This is the interesting part, because talking about uncertainty, you can't write an uncertainty budget unless you know everything that affects the measurement. Most labs don't do uncertainty because they don't know everything that will affect the measurement. You can look at simple budgets with 2 things. You look at an NMI budget like ours and you see a page full of things. There's none in between for like really normal people in a normal lab. And so yes, no one does an uncertainty budget. Well, my group and I argue all the time. It's fun as long as you buy the beer I'm willing to talk about uncertainty. So, one of the problems is, where are you going when you hit the wall? Basically, there's always a deflection. You may go a little too far, and you end up with, you hope, the right answer. But again, you go in and you come out again. If it hits and it slides, then the answer you get is close to the right answer. It's a cosine error. But we're talking about such tiny distances, you can get a fairly big angle like this. If you're measuring something really, really big, like a 1 millimeter hole, you're not going to see that sentence many places, but if it's really big, you don't have too much of a problem. When you get down to tiny, tiny clearances, then you start to have problems. And if you do it completely wrong, you could pick up 50 nanometers, which is half a 10th micrometer. The next thing is, the probes themselves aren't always circular. The old CMM probes on touch fire classically had a 3-lobed. They measured something really, really round. It would measure it had 3 lobes because of internal to the probe, the mechanisms weren't squared up and they did funny things. These were all studied and modeled and all that good NIST stuff. And you can see the sort of errors you get. Again, 20 nanometer type stuff. Now, the probe tip also might be 8-shaped. How do you put a 30 micrometer sphere on the end of, let's say, well, big sphere, 100 micrometer sphere on 70 micrometer? Can you glue it? And how round is the sphere? So we have all sorts of little machines that can bring the glue in and touch it and hold on to the sphere, but of course they're not always round. Now you can check that when you measure a really good sphere, but as you're moving, you may well hit here instead of here where it should go. Again, that's a small error, but it's not trivial. And again, you can do it in software afterwards. Again, you have to know where the thing is pointed when you hit the hole. One of the biggest problems with coordinate measuring machines is all it tells you is the probe hit something. It doesn't say whether it's a wall this way or that way. All it says is, I hit something. You don't know where on the ball you hit. So unless you know the shape of what you're trying to measure, the numbers mean nothing. We find that causes all sorts of mischief in just CMM measurements. In many cases, we measure the same thing with an 8 millimeter ball, a 4 millimeter ball, 1 millimeter ball, and a half millimeter ball, and project the answer down to a 0 millimeter ball in order to get rid of this damn effect. That's in the big machine. We've gotten rid of most of these things. We iterate a lot. You try something and it fails. You fix something, you try something else, and it fails. In general, whenever I build something, the third one works, which means you have to fail twice very quickly or you get way behind schedule, because you're going to screw it up twice. Physicists, engineers, some of them try to do it right the first time, like NASA. Endless problems trying to do it right the first time. I would have lost hundreds of astronauts right now. Yes, it's unfortunate. We won't talk about the probe comp because it's a problem, but dirt is a problem. It's hard to clean a little hole. We've tried like sprays that use basically frost, we do icicles and knock them down. Compressed air, ultrasonic baths, this and that. Sometimes it works, sometimes it doesn't. This typically is no bigger than 50 micrometers, which means the dirt that matters is a micrometer. And so what happens? Well, dirt can actually get pushed. I mean, the force is in micronewtons, but it can move. Sometimes it can just get squished. We don't know what the hell dirt is actually. There's not enough of it to characterize other than you get the wrong answer. If you come in really fast and you put a big force like a millinewton or 20 or 30 millinewtons, then it can actually break whatever it is, and then something happens and then it works right, because you've broken it and it's fell away. These are particles you find in the air. Some of them organic, some of them aren't. I guess the probe can actually get a virus and be sick, or at least give you the wrong answer. Fibers aren't so bad. Again, we're not talking about fibers in the sense of your hair. We're talking about fibers that are less than a micrometer by a lot. And of course, you can mess up everything by having no bone. Keeping things clean is very difficult. And that's one of the problems we have. We're busily making Model 3 of the probe that doesn't use a glass fiber, it uses a metal fiber. And so the insides are a bit different. Because glass is hard to make round. Now, to do Z is actually quite easy. The fiber is so thin that when you come straight down into something, it goes boink in milliseconds. It basically pops up. And so now you know you've hit something with really good sensitivity, even better sensitivity than X and Y. You actually see the sensitivities better in Z. And since these things are long and thin, they don't break, they just bend. Glass is extremely tough when it gets really, really small. And so here we're talking about forces of about 2 millinewtons, which for this probe is a lot of force. And so the buckling actually is almost linear itself. So if we wanted to, you could make this a 3D probe. We don't really have any customers who have 3D fittings. This is a fuel injector like you would have in your car. People are interested in the shape of the hole. Down there on the right is the shape of that hole as you go inside of it. There's the probe, and there's the probe ball. Down at the bottom, those are micrometers. So it ends up being about 40 micrometer and then smaller hole. So this is it again on the machine. Now, the next thing is it sticks for who knows reason. And the people I work with, they're terribly clever people. They decided, well, if it sticks, maybe we could shake it loose. So they literally put a buzzer here that would vibrate it and maybe let go of the surface. And it works most of the time. It's very cool to have the buzzer, because you can, well, they can hear it. I can't hear a damn thing with that frequency, but regular people can hear it. And so we've tested it, doing things like roundness with the buzzer and the part. It's hysterical what you can do with this thing. And there's the probe going down into a hole. Hole 127 micrometers in diameter. You can measure down 6 millimeters down. That's just the taper of the fuel nozzle. This is another test which took lots and lots of data in 3D to generate what is in fact, well, that makes it funny looking, but it's kind of a sphere. This is supposed to be a hemisphere. It's supposed to be 20 degrees. And again, you can go in there. Externally, you can do a really good job. Because the probe, you can't make the probe bigger than the hole and have it work. So, with this probe and the machine that's on, and the machine, by the way, has a positioning accuracy of 20 nanometers. So anywhere in the volume of the machine, I can put the end of the probe within 20 nanometers of where I want it. The machine does have a travel of 1.2 meters, 800 millimeters, and 400 millimeters. It's kind of a big machine for this, but it's the only one we have with that kind of precision. Nothing's better than the Moore machine. And so you make holes. We measure holes. So we're going to have a good time. Any questions? I know, where nanometer stuns people into silence. It's quite interesting. But in our labs, depending on who I'm talking to, if the new buildings people say a tenth, they mean a 10th micrometer. Yeah. If the thread people say a tenth, they mean a 10th of a mil. You don't want to get mixed up when you talk to them. But the next probe so far is a bigger tip, but it'll be, we could go down pretty much 2 or 3 centimeters down into a hole. Biggest job we have at the moment is spectroscopists have these little cuvettes, which looks like a waveguide, but it's made out of glass. It's a 1 millimeter slot in glass. And they want to know the distance between the glass all the way to the bottom. They would like an accuracy of 0, because they are, but we're hoping to get down below 100 nanometers on that. With some luck, they'll have that up on the machine this week. Good. Thank you.
Thank you, Ted. Well, I think that concludes the meeting for today. So I appreciate all you coming out, and I want to say thank you again to Lenox Laser. You guys were our gracious hosts, and everything was really nice. A very interesting lab, and I know all of us enjoyed seeing it. So if there's no other, door prizes, yes. Pete, I'm going to send you to the back. On the bottom shelf of that right tier thing, there are the slips you've made. We have 3 door prizes to give away. They're on the bottom shelf of that. Did you see them? Draw the first name.
Rachel Hoffman.
Yeah, she's not perfect. I get a mug. I love mugs. Thanks, guys.
The gift card works again.
Cloud Dane. Did I say that right? And Tom Larson.
Hey, Tom!
All right, and with the door prizes out of the way, I appreciate everyone coming again. And let's give one more round of applause for Lenox Laser.
And everybody else, including the press, please, we have some cookies and donuts right here.
Get a sugar high. Yeah.